we begin the session, let us recall an important theorem which we are going to make use of while proving some of the results. Theorem 8.3. Let P be a prime number if P divides A square, then P divides A, where A is a positive integer. Also, let us recollect the following. If an integer A is divisible by an integer n, then we can write A equals nk for some integer k. If A is divisible by 2, then A equals 2k. If A is divisible by 3, A equals 3k. If A is divisible by 5, then A equals 5k, and so on. Also, if two positive integers do not have any common factor or factors, then they are called co-prime integers or simply co-primes. HCF of co-primes is 1. For example, 2 and 5 are co-primes. 6 and 35, they are also co-primes. Note here that 6 is not a prime number. 35 is also not a prime number. But since 6 and 35 do not have any common factor, they are co-primes. 8 and 9, 10 and 21, these are some other examples for co-primes. Now, to prove root P is irrational where P is a prime number. What do you mean by a prime number? A number which has no factors other than 1 and itself is called a prime number. For example, 2, 3, 5, 7, 11 and so on are prime numbers. We need to prove here that root 2, root 3, root 5, root 7, etc. are irrational numbers. Let us consider some examples. Example 1. Prove that root 2 is irrational. We prove this result by contradiction. We assume that the given statement is false, and then proceeding further, we come to a conclusion that our assumption itself is wrong. This method of proof is called proof by contradiction. Let us assume to the contrary that root 2 is rational. Let root 2 equals a over b, where a and b are integers, b not equal to 0, that is denominator is not equal to 0, a and b are co-primes. Bring b to the left hand side. Root 2 into b equals a, squaring both sides. Root 2 into b whole square equals a square. Root 2 into root 2 is 2, b into b is b square. 2b squared equals a square. Take this as equation 1. This means that a square is divisible by 2. So, a is also divisible by 2 by theorem 8.3. Let a equals 2k, where k is some integer. Let us square both the sides. A squared equals 2k whole squared. A squared equals 2k into 2k is 4k squared. Take this as equation 2. From equations 1 and 2, we can conclude that 2b squared equals 4k squared. 2 is a common factor here. 2 ones are 2 twos are. Therefore, we get b squared equals 2k squared. This means that b squared is divisible by 2. So, b is also divisible by 2. Look at these two statements. A is divisible by 2 b is also divisible by 2. Therefore, 2 is a common factor for a and b. This contradicts our assumption that a and b are co-primes. This contradiction arose due to our wrong assumption that root 2 is rational. Therefore, root 2 is irrational. Similarly, let us take one more example. Prove that root 5 is irrational. The proof is very similar to that of the previous one. Therefore, I will go through this proof quickly. Let us assume to the contrary that root 5 is rational. Let root 5 equals a over b. Bring b to the left hand side. Root 5 into b equals a. Squaring root 5 into b whole squared equals a squared. 5b squared equals a squared. Take this as equation 1. This means a squared is divisible by 5. So, a is also divisible by 5. Let a equals 5k. Then, squaring both the sides, a squared equals 5k whole squared. A squared equals 25k k squared. Take this as equation 2. From equations 1 and 2. In place of a squared, substitute 25k squared from 2. Then we get 5b squared equals 25k squared. 5 is a common factor here. 5 ones are 5 5s are. We get b squared equals 5k squared. This means b squared is divisible by 5. So, b is also divisible by 5. Look at these two statements. A is divisible by 5. B is also divisible by 5. Therefore, 5 is a common factor for a and b. This contradicts our assumption that a and b are co-primes. This contradiction arose due to our wrong assumption that root 5 is rational. Therefore, root 5 is irrational. Similarly, we can prove root 3 is irrational. Here we get 3 as a common factor for a and b. We can prove root 7 is irrational. Similarly, here we get 7 as a common factor for a and b. Now, let us prove the algebraic sum of two irrational numbers is irrational. Let us take an example. Prove that root 2 plus root 3 is irrational. We know that root 2 is irrational, root 3 is irrational. We need to prove that their sum is irrational. Again, let us assume to the contrary that root 2 plus root 3 is rational. Let root 2 plus root 3 equals a over b, where a and b are integers, b not equal to 0, a and b are co-primes. From now on, I will slightly deviate from the usual method. The usual method is we bring one of the terms on the left hand side to the right hand side. Instead, first I will multiply the left hand side by b. I will bring b to the left hand side like this. Root 2 plus root 3 into b equals a. The advantage of this method is that we can avoid dealing with fractions. Now open the brackets. Root 2b plus root 3b equals a. Now bring one of the terms on the left hand side to the left hand side, right hand side. I am bringing root 3b here. Root 2b equals a minus root 3b. Squaring both the sides, we get root 2b whole square equals a minus root 3b whole square. Left hand side is root 2 into root 2, that is 2, b into b is b squared, 2b squared. The right hand side, the expression on the right hand side can be simplified, can be expanded using this identity. A minus b whole squared equals a squared plus b squared minus 2ab. Here, in place of a, we have a. In place of b, we have root 3b. Therefore, a squared plus root 3b whole squared minus 2 into a into root 3b. Simplifying this further, 2b squared equals a squared plus 3b squared minus 2ab into root 3. Here, the last term contains root 3. We need to express the equation in terms of root 3. But the term containing root 3 is having negative sign. So, to make it positive, let us bring that term to the left hand side and then 2b squared to the right hand side, like this. Plus 2ab root 3 equals a squared plus 3b squared minus 2b squared. 3b squared minus 2b squared, they are like terms. Their sum is 1b squared. Their algebraic sum is 1b squared. 2ab root 3 equals a squared plus b squared. Root 3 equals a squared plus b squared whole divided by 2ab. Since a and b are integers, a squared plus b squared and 2ab are integers. Let a squared plus b squared equals s, 2ab equals t, where s and t are some integers. Therefore, root 3 equals s over t. This means that root 3 is rational. But we know that root 3 is irrational. 3 is a prime number. Root of a prime number is irrational. This is a contradiction. This contradiction arose due to our wrong assumption that root 2 plus root 3 is rational. Therefore, root 2 plus root 3 is irrational. Example 4. Prove that root 7 minus root 5 is irrational. The proof is very similar to that of the previous one. Let us go through the steps quickly. Let us assume to the contrary that root 7 minus root 5 is rational. Let root 7 minus root 5 equals a over b. Bring b to the left hand side. Open the brackets. Root 7b minus root 5b equals a. Now, you can bring either of the terms on the left hand side to the right hand side. It is convenient to bring minus root 5b to the right hand side, because if you bring root 7b to the right hand side, then root 5b has negative sign, and to get rid of that sign, we need to multiply the entire equation by minus 1. To avoid that, let us bring minus root 5b to the right hand side. Squaring both the sides, we get this. Use this identity to expand the right hand side. Root 7 into root 7 is 7, b into b is b squared, a squared plus root 5b whole squared plus 2 into a into root 5b. 7b squared equals a squared plus 5b squared plus 2ab root 5. Now, the term containing root 5 has positive sign. Therefore, keep the term where it is. Bring a squared plus 5b squared to the left hand side. 7b squared minus 5b squared minus a squared equals 2ab root 5. 7b squared minus 5b squared is 2b squared. Now bring 2ab to the left hand side. 2b squared minus a squared divided by 2ab equals root 5. Now swap the sides. Root 5 equals 2b squared minus a squared divided by 2ab. Since a and b are integers, 2b squared minus a squared and 2ab are integers. Let 2b squared minus a squared equals s and 2ab equals t, where s and t are some integers. So root 5 equals s over t. This means that root 5 is rational, but we know that root 5 is irrational. 5 is a prime number. Root of a prime number is irrational. This is a contradiction. This contradiction arose due to our wrong assumption that root 7 minus root 5 is rational. Therefore, root 7 minus root 5 is irrational. Now, let us prove algebraic sum of rational and irrational is irrational. Let us take an example. Prove that 4 plus root 3 is irrational. Let us assume to the contrary that 4 plus root 3 is rational. Let 4 plus root 3 equals a over b. A and b are integers, b not equal to 0, and a and b are co-primes. Bring b to the left hand side. Open the brackets. 4b plus root 3b equals a. Now bring 4b to the right hand side. Root 3b equals a minus 4b. Root 3 equals a minus 4b divided by b. Since a and b are integers, a minus 4b is also an integer. Let a minus 4b equals s, where s is some integer. Therefore, root 3 equals s over b. This means that root 3 is rational. But we know that root 3 is irrational. This is a contradiction. This contradiction arose due to our wrong assumption that 4 plus root 3 is rational. Therefore, 4 plus root 3 is irrational. Example 6. Prove that 5 minus root 2 is irrational. Let us assume 5 minus root 2 is rational. Let 5 minus root 2 equals a over b. Bring b to the left hand side. Then open the brackets. 5b minus root 2b equals a. Now bring minus root 2b to the right hand side and a to the left hand side to get rid of the negative sign of root 2b. 5b minus a equals plus root 2b. Now plus root 2b equals 5b minus a. We have swapped the sides. Plus root 2 equals 5b minus a over b. Since a and b are integers, 5b minus a is also an integer. Let 5b minus a equals s, where s is some integer. Root 2 equals s over b. This means that root 2 is rational, but we know that root 2 is irrational. This is a contradiction. This contradiction arose due to our wrong assumption that 5 minus root 2 is rational. Therefore, 5 minus root 2 is irrational. To prove product and quotient of a rational and an irrational is irrational, consider this example. Prove that 5 root 3 is irrational. Let us assume that 5 root 3 is rational. Let 5 root 3 equals a over b. Bring b to the left hand side. 5b root 3 equals a. root 3 equals a over 5b. Since a and b are integers, 5b is also an integer. Let 5b equals s, where s is some integer. Root 3 equals a over s. This means root 3 is rational, but we know that root 3 is irrational. This contradiction arose due to our wrong assumption. Therefore, 5 root 3 is irrational. Example 8. Prove that root 7 by 3 is irrational. Again, let us assume root 7 by 3 is rational. Let root 7 by 3 equals a over b. On cross multiplying, we get root 7 into b equals a into 3. b root 7 equals 3a. Root 7 equals 3a over b. Since a and b are integers, 3a is also an integer. Let 3a equals s. Root 7 equals s over b. This means root 7 is rational. But we know root 7 is irrational. The contradiction arose due to our wrong assumption. Therefore, root 7 over 3 is irrational. Example 9. Prove that 2 over root 5 is irrational. Again, let us assume that 2 over root 5 is rational. Let 2 over root 5 equals a over b. On cross multiplying, we get 2 into b equals a into root 5. 2b over a equals root 5, which implies root 5 equals 2b over a. Let 2b equals s, then root 5 equals s over a. This means that root 5 is rational, but we know root 5 is irrational. The contradiction arose due to our wrong assumption. Therefore, 2 over root 5 is irrational. Now, some miscellaneous examples. Example 10. Prove that 3 root 2 plus 2 root 3 is irrational. Let us assume to the contrary that 3 root 2 plus 2 root 3 is rational. Let 3 root 2 plus 2 root 3 equals a over b. Bring b to the left hand side and open the brackets. 3b root 2 plus 2b root 3 equals a. 2b root 3 equals a minus 3b root 2. Squaring both the sides, we get 4b square. 2b into 2b is 4b squared. Root 3 into root 3 is 3 equals a square plus 3b root 2 whole square minus 2 into a into 3b root 2. 12b squared equals a squared plus 3b into 3b is 9b squared. Root 2 into root 2 is 2. 9b squared into 2, then minus 6ab root 2. 12b squared equals a squared plus 18b squared minus 6ab root 2. Bring minus 6ab root 2 to the left hand side to get rid of the negative sign, to make it positive. Equals a squared plus 18b squared. Bring 12b squared to the right hand side minus 12b squared. Plus 18b squared minus 12b squared is plus 6b squared. Root 2 equals a squared plus 6b squared over 6ab. Since a and b are integers, a squared plus 6b squared and 6ab are integers. A squared plus 6b squared equals s and 6ab equals t. S and t are some integers. Therefore, root 2 equals s over t. This means that root 2 is rational, But we know that root 2 is irrational. This contradiction arose due to our wrong assumption. Therefore, 3 root 2 plus 2 root 3 is irrational. Example 11. Prove that 6 root 5 minus 3 root 7 is irrational. Let us assume 6 root 5 minus 3 root 7 is rational. Let it be equal to a over b. Then bring b to the left hand side. Open the brackets like this. Now let us bring minus 3b root 7 to the right hand side. Then it will become positive. Squaring both the sides. To expand the expression on the right hand side, use this identity. 36b squared into 5 equals a squared plus 3b root 7 whole squared plus 2 into a into 3b root 7. 180b squared equals a squared plus 9b squared into 7 plus 6ab root 7. 180b squared equals a squared plus 63b squared plus 6ab root 7. Transfer a squared plus 63b squared to the left hand side. 180b squared minus 63b squared minus a squared equals 6ab root 7. 180 minus 63 is 117. 117b squared minus a squared equals 6ab root 7. 100b squared minus a squared over 6ab equals root 7. Root 7 equals 117b squared minus a squared over 6ab. Let 117b squared minus a squared equals s, 6ab equals t. Therefore, root 7 equals s over t. This means root 7 is rational. Here is a contradiction. This contradiction was due to our wrong assumption. Therefore, 6 root 5 minus 3 root 7 is irrational. Last example. Prove that root 5 plus root 6 is irrational. Note here that 5 is a prime number, 6 is not a prime number. We have proved root 5 is irrational, but we have not proved root 6 is irrational. Therefore, while proving this result, we make use of the fact that root 5 is irrational. Let us assume the given number is rational. Let root 5 plus root 6 equals a over b. Bring b to the left hand side. Open the brackets. Now, you cannot bring root 6b to the right hand side. You have to bring root 5b to the right hand side. Squaring both the sides. Make use of this identity and expand. 6b squared equals a squared plus root 5b whole square minus 2 into a into root 5b. 6b squared equals a squared plus 5b squared minus 2ab into root 5. Since 2ab root 5 has negative sign, transfer that term to the left hand side to make it positive and bring 6b squared to the right hand side. 2ab root 5 equals a squared plus 5 minus 6 is minus 1, therefore minus b squared. Root 5 equals a squared minus b squared over 2ab. Let a squared minus b squared equals s. to AB equals T. Then root 5 equals S over T. This means that root 5 is rational. But we know that root 5 is irrational. The contradiction arose due to our wrong assumption. Therefore, root 5 plus root 6 is irrational. Let us have a discussion on some other topic in the next session. Till then, bye.